Hi, my name is Natalie Goddard, and my project is titled Extreme Deformation of Polymers under the Supersonic Laser-Induced Projectile Impact Test, also known as LIPIT. I would like to thank my mentor, Dr. Ned Thomas, and Dr. Jin Ho Hyun for also helping me on this project. So my goal for the summer is to help my mentors write and submit a review article for the journal Soft Matter by September 1st. In this article, we plan to discuss the LIPIT apparatus, integrate existing work, and provide direction for the future. Most of my work this summer has been on this middle stage of integrating existing work and has involved summarizing and organizing previous publications in order to see how to best represent them in our review article. My presentation today will follow a similar setup, beginning with discussing the LIPIT apparatus. LIPIT is an extreme strain rate test causing materials to undergo strains on the order of 10 to the 6th to 10 to the 8th inverse seconds. In LIPIT, a laser pulse is shot at a thin gold film, producing a plasma. This plasma then expands a PDMS film, shooting a silica projectile at a substrate. This substrate is mounted on a TEM grid. The projectile can reach speeds of up to 1 kilometer per second. Some advantages of this test over other mechanical tests is that it is miniaturized, so we can have more tests in a relatively short amount of time. Additionally, it only requires a small projectile and sample, and because it is on this TEM grid, it can be rapidly characterized. Backing up a little bit to talk about high strain rate deformation. So strain in this case is the extent of polymer deformation, and strain rate is the change in this strain with respect to time. This diagram gives a better idea on how different strain rates relate to everyday activities. Again, LIPIT is on the order of 10 to the 6th to 10 to the 8th, so we are in this ballistic test to extreme condition region. This corresponds to both applications in bullets and aerospace. Additionally, we can think of silly putty to see how polymers perform under different strain rates. At relatively low strain rates, we know that silly putty thins out and performs ductilely when you pull it very slowly apart. However, when you pull it apart very quickly, we know that it fractures brittly. This is because the chains do not have enough time to react to the stress. This graph here shows different mechanical tests and the strain rates that they explore. I wanted to point out the quasi-static region with the standard tensile test because a lot of people are familiar with this test. LIPIT is all the way at the top of this diagram in the shock region. There are other tests that can reach some strain rates that LIPIT can, including the Taylor impact test and plate impact test. However, LIPIT goes beyond these tests to reach 10 to the 8th inverse seconds. Some applications of these high strain rates include protection against bullets in body armor for soldiers, cold spray, which is a coating and additive manufacturing process where particles are shot at a substrate, and lastly, protection against micrometeorites for spacecraft orbiting the Earth. A challenge that we have with LIPIT is how to compare the performance across different substrates. In order to do this, we define the specific penetration energy. Penetration energy is the amount of energy that the film absorbs as it is impacted by the projectile, and is defined as the change in kinetic energy with a minor consideration due to the energy of the drag of the projectile. When we divide the penetration energy by the mass of the plug, which is the amount of the film that travels with the projectile as it exits the film, we find the specific penetration energy, which we can compare across substrates and thicknesses. We will see later that these thin films have superior specific penetration energy, and this is due to the entanglement network of these polymer thin films. To think about polymer entanglements, we can think about a bowl of cooked spaghetti. If we have a bowl of very long spaghetti, say 100 kilograms per mole, you can imagine how pulling one of these spaghettis would impact all of the entangled spaghetti noodles around it, thus dissipating and involving more polymers and dissipating the energy better. However, if we had a bowl of short cooked spaghetti, say 10 kilograms per mole, pulling one of these strings would have little effect on the rest of them, and thus the energy could not be dissipated, involving more of the spaghetti chains. Similarly, polymers' performance under these experiments depend on the entanglement network of the film. Additionally, when these films are confined to very thin heights, we have geometric confinement effect. So these surface chains here are actually entangled less than the bulk in the middle. And this actually leads to higher mobility of these chains highlighted here in red, which we will see leads to higher specific penetration energy. So now I will discuss 3 different substrates and their performance after doing lipid experiments on them. First, starting with polystyrene. Polystyrene is brittle at room temperature, and we see evidence of this brittle fracture in these radial crazes and tangential crazes, which are basically micro cracks. However, more surprisingly, we see these thermally softened regions and this volcano shape on the exit surface. This is evidence of ductile fracture and is due to adiabatic heating, which locally rises the temperature above the glass transition temperature and leads to this stretching and enhanced energy absorption. We will also be looking at polymer-grafted nanoparticles. These are one-component nanocomposites, which polystyrene is covalently anchored to these nanoparticle cores. In addition to the entanglements from the polymer chains to retard the projectile, these nanoparticles provide a nodal network to help dissipate the energy. There are lots of variables that affect the performance of these thin films, including the radius of these nanoparticles, the number of chains anchored to each nanoparticle, and the chain length attached to each of the nanoparticles. We can see in this image here with very short chain lengths, around 20 kilograms per mole, this film does not dissipate energy very well because the projectile is about the same size as the hole that it perforates. However, down here we see that these films with much higher polymer chain length on 231 kilograms per mole perform much better and dissipate the energy much beyond the hole that the projectile creates. Lastly, we will talk about multi-layer graphene. These SEM images show petals, cracks, and radial folds. The number of petals increases as the speed of the projectile increases from 600 to 900 meters per second. Multi-layer graphene is known for its high strength, stiffness, and structural anisotropy, which helps it perform so well under these high strain rate experiments. And this fact can be taken advantage of as more people develop graphene nanocomposites at a large scale. So finally, we will compare the specific penetration energy of these 3 thin films. The polymer-grafted nanoparticles is shown here in pink, the homopolystyrene thin film is shown here in black, and the multilayer graphene is shown here in maroon. We see that all 3 of these thin films perform better than the macroscopic materials of Kevlar, aluminum, and stainless steel. In these high velocity regions, the homopolystyrene sheets and the polymer-grafted thin films actually perform between 5 and 6 times better than these materials of steel and aluminum. The polymer-grafted nanoparticle has the highest specific penetration energy of the thin films because the entanglements and the nodal network is working together to help dissipate energy. These films have such superior specific penetration energy because the specific penetration energy relates the strength to the density and the thickness of the film. So these high specific penetration energy films can especially be used in applications where being lightweight is important, such as applications in military and space. So some future directions for LIPIT. One question is how these results scale and how they can be used to produce products to dissipate energy in these different applications. One question that addresses this is to see whether 10 layers of a 10 nanometer thin film performs better versus a single 100 nanometer thin film. Additionally, right now we are only taking in translational kinetic energy into consideration, so we could take in rotational kinetic energy, considering the projectile rotating as it is flying towards the substrate and it possibly wrapping around the film as it impacts it. Additionally, we can always test more soft matter substrates, including block copolymers and self-healing polymers. So that is the end of my presentation. Thank you so much for listening. And I just wanted to thank everyone involved in the online OREU program this summer at Texas A&M. It has been an invaluable experience, and I am so excited that I got to be a part of it amidst COVID-19. Thank you so much.